So it's a great pleasure to have Jean here presenting his work. Jean joined the computer science department in Stony Brook 6 years ago. Before that, he was working in graphics at George Washington University. He has also worked in industry in Peru, where he's from. Jean started working in our group about 5 years ago on the problem of structured learning. Now, probably not everybody knows what structured learning is. Jean will explain that, but I will just say that it is important for us to be able to relate probabilistic variables, for us to be able to relate things for which we have evidence but not certainty over large amounts of data. Jean will explain how this is being done. He has worked initially on data that comes from brain scans, trying to relate the behavior of different regions of the brain as we're getting functional brain scans. But his work is much more general than that. He has come up with a number of algorithms that can be applied to different data sets, anything from the stock market to human heartbeats. He will talk about all those things. Even more important, Jean he's close to graduating. He has already become a researcher on his own. He's been publishing work that is outside the traditional work in our lab, where he's exploring important theoretical properties of a number of algorithms, and we expect that this work will be of importance to the whole field of machine learning, especially when it comes to large data sets. A brief note is that Jean was able to take a lot of the concepts and move away even from probabilistic models to game theoretic models. I don't think you will have time to talk about this today, but it's another very important aspect of his thesis. So, and I think with that, I'll let Jean start.
Thank you. So I'm John Honorio. I'm from the Image Analysis Lab from the Computer Science Department. My advisor is Dimitri Samaras. My co-advisor Luis Ortiz. We have been working also about the game theoretical models with Luis. My collaborators from the neuroscientific field are Rita Goldstein from Brookhaven National Lab and Hoishan Leon. So I will try to first explain what are graphical models, why these models are important for different areas. I will explain what inference and learning means in the context of graphical models. We'll talk about priors and regularizers since this is one of the main parts of my presentation. And then as technical contributions, I will show some theoretical properties. For instance, convergence or positive definiteness of the solutions that we get. I will talk about algorithms, for instance, the quadratic knapsack that we can arrive to after doing some change of variables from our original problem. And also, I will show you some experimental validation in different data sets, including brain fMRI, gene expression data, stock prices from the NASDAQ market, and world weather. So I hope everybody may get flavors from different aspects. So you might like one thing more than the other, and I hope everybody will be happy with this presentation that has several sides. So let me show you first a motivating example that I have borrowed from Frey and Jojic in 2005. Imagine we have the problem of separating face from background. So we have different pictures, and these pictures is perhaps the same face as you see here, and they're different backgrounds, or the same background for different faces. So how can we model this in a computer as a generating process, right? So as a generating process, I might say, okay, I take a face, and I have a mask saying where this face falls in, and then I have a background, and if I put these three things together, I can generate an image. So that's an easy problem, the generation of an image given the face, the mask, and the background. And you can use any regular software for doing these type of things. But then the more interesting problem is, can we make a computer guess the face and the background from an image? So if I have it as an input an image, can I guess the face and the background? Can I do that separation? So that's a more interesting problem. And we can use, for instance, graphical models for this type of tasks. Of course, this is just a motivating example. It's a very simple problem. Let me show you a little more interesting problem. This is the problem of illumination, shadow, and geometry estimation. This is the work from another member of the image analysis lab, which is Alex Panagopoulos, and this is work under submission. So imagine I know the geometry of the object, I know the illumination properties, such as the location of the light, the direction of the light, and then I know also the reflectance properties of the materials in the object of importance. Given these three things, I could generate an image. For instance, this type of image that might be kind of complex to generate. But a more interesting problem is, if I give you this image as an input, can you guess what is the geometry of the main object that you have in this image, which is the car? So we can get this geometric shape here, and can we guess also the illumination? So if I just notice that we have introduced some pole here, and you can see there is a shadow of the pole, and the shadow of the pole was actually estimated in this case from the shadow that you can observe in the original image. So it is not only recovering the shape, the geometric shape of the object, but also the illumination properties and the direction of the light in this case. So these type of problems, as you have seen in the previous example, you can also solve them by using the graphical models. Let me show you another work of another person from our lab, which is from dense surface tracking. So the motivating problem here is, if I have 3D scans of the face, so it's not an image, but you have the depth for the different places of the face, then if I have that, can I put this type of mesh across time? So while the person is doing different expressions, I am recording and I am generating this mesh, and then I can use this mesh in order to animate some character. For instance, if you can relate to maybe the movie Avatar, and if I capture this expression, I could generate one of the animated characters in the movie Avatar. And this can also be solved by using graphical models. So let me explain what graphical models are. These models will describe the topology of the components. As you have seen in the previous slide, I was showing some arrows saying how different parts of the model are generated by using different parts of the model. So these are components in a complex probability model, and by components we mean variables or nodes, and by topology we mean the dependencies or edges in our case of graphical models. And there are several different flavors of graphical models. One of them are Bayesian networks. Then we also have Markov random fields and factor graphs. So let me introduce first Bayesian networks. These Bayesian networks are directed acyclic graphs. So we have arrows, and there are no cycles in the arrows. So if you start following the arrows, you never end up in the same node. So if this arrow were pointing the other way, then we would have a cycle, and then this wouldn't be a Bayesian network. So these are directed acyclic graphs where nodes are the random variables, the components that we are trying to model, and the edges mean dependency. The important thing here is that this graph and arrows are defining a joint probability distribution, where the joint probability is the multiplication of the probability of every node given its parents. So if you want to show this as a formula, you will have P of x1, because x1 doesn't have any parents, multiplied by the probability of x2 given x1, because the only parent of x2 is x1, and so on and so forth. You can see how here x4 has a parents x1, 2, and 3. So you have the three parents here. So this This graph is actually showing the probability of all the joint probability of all the variables as factors being multiplied, and that's what the graphical model is trying to model. I will go later. And why do we do that? Well, then we will have to introduce a little bit of the concept of conditional independence, but I will do that later. And as I shown in my motivating example, you might talk about phase and the mask, and here you can read it as the mask depends on the phase, the image is defined by the phase, the mask, and the background, and so on and so forth. So the parenthood means that this variable here depends on the parents. Then the other type of model is Markov random fields. In this case, we have a directed graph, so they don't have arrows; they are just edges. And there is one function per click. So let me quickly introduce the definition of click. So click is a set of nodes such that for every 2 nodes in that set, there is an edge connecting them. So if you take these 3 nodes here, there is one edge between any of the pairs of nodes in this set. If you take this, you might notice that there is an edge, there is a line connecting any of the 2. Now, if you take the 4 of them, there is a missing edge here, so the 4 of them are not a click because we don't have this edge. So in the case of Markov random fields, we have one function per click. Let's call that function G1 for the click 1 and G2 for the click 2. And the probability function is just the multiplication of the two functions per click. But the important thing here is, unlike for Bayesian networks in which we are multiplying probabilities, therefore, if all the p's were probabilities, we multiply them and the output will be a probability. In this case, we are multiplying functions. That means that it is we don't get a probability, and in order to get a probability, we want to fulfill this property that for all possible values of the variables, if we integrate over all possible values of the variable, or if we do a sum over all possible values of x, then we should get 1. And in this case, we will not get 1. If we don't have the c here, we will not get 1. So that what we do is we define c as just the summation of all the multiplications of the variables, and then when we divide this value here, we get a p of x that is a probability function. So, and this constant c here is what is called the partition function. And one important point to make is that in general, this partition function is intractable, meaning that in general, it takes exponential time to compute this function, and therefore it is hard for a computer to compute. Just think about it, if you have 100 variables, it might take, and you have 100 binary variables, it might take 2 to the power of 100 steps to compute this summation. So that's a lot of time for a computer to calculate this value. And that is one problem of using these Markov random field models for some specific cases. But happily, this partition function is computable for some cases in which I am focusing in this talk. So let me introduce the concept of conditional independence. And conditional independence is that if we have 2 events A and B, they will be conditional independent given some other event S, such that if we know, if S is known, then the knowledge of whether A occurs provides no information on the likelihood of B occurring. So you can think about, for instance, event A being me getting good grades in a course, and event B being an earthquake in some country. So I can know that if I get good grades, that doesn't tell anything about an earthquake in some country, and if an earthquake in some country happens, that doesn't mean that I will get good grades, right? So one variable doesn't give you any more information on the other variable. But you can think, for instance, about event A being me smoking, and event B being me having lung cancer at the age of 60. So we might know that if I smoke, then my likelihood of having lung cancer will be higher. And if I don't smoke, my likelihood of having lung cancer will be lower. So those 2 variables are not conditionally independent, as given by this definition. And we can express that in this way: A and B are independent given S, or also in this way that A and B are independent, so that we can separate this probability as the multiplication of 2 probabilities. And you can see how these formulas are similar to the formulas that I was showing before for Bayesian networks for instance, in which we had these sets of parents. And now there is another interesting concept, important concept in graphical models, which is the concept of Markov Blanket. And we say that a node is independent of the rest of the variables when we are given the Markov Blanket. So this variable in the center is only dependent on the neighbors in the case of MRFs in the left, and this variable in the center is only dependent on the parents, the children's, and the children's parents, and not in any other variable that are in our graphical model. So the graphical, and similar in this case also, it's not depending on any other variable. So once you know the neighbors, you don't need any more information from the graphical model. So you can see how the graphical model is actually defining a set of conditional independence properties in the model. Now, let me relate to inference and learning. Inference is the problem that given a structure, so if I give you this set of nodes, I give you the structure, I give you the edges, and let's assume I give you the weights of the edges, and this defines a graphical model. So given this structure, the parameters which are the edge weights, and possibly some node values, so I'll tell you that x1 equal to 10 and x2 equal to 5, then inference is the problem of finding the best, which might mean the most probable setting of the other nodes. And you can see, for instance, the initial motivating problem of guessing what the face and the background is from an image fits into this context in which the given values are the image, and then you want to guess the face and the background. So that's the problem of inference, and the problem of my colleagues in the group of Alex Panagopoulos and John Sen that I showed you in the beginning also fits in this problem of inference. So the graph is given, the edges are given, and the weights of the edges are given, but we can have a second layer problem in which we call it parameter learning, and then here we are only given the structure, we are given training data, we are given a set of examples from which to learn, and the problem is to find the best setting of the parameters. So what are the weights of these edges? That's the parameter learning problem. So the topology is known, but the weights of the edges are not known. And then there is another problem that we call structured learning, in which we are given training data. So we know that these variables exist. We have values for these variables. We have several examples from which to learn, but we don't know what are the edges of this structure, and we don't know what are the weights of the weights of the edges of this structure. And this is the focus of my PhD, and I am trying to create tractable problems and different priors for this problem. Yet another motivation, besides the fact that we can learn structures, for instance, in problems in which we don't know the structure, and then we can use it for doing inference and solving this interesting problem. Another motivation is to understand, for instance, brain connectivity. Let me briefly introduce what brain fMRI is. In brain fMRI, we have the fact that activated brain regions will show a change in blood supply. So every time you have a region of your brain working, that region uses the oxygen that it has, and then it has to ask for more oxygen. So there is a blood flow to that specific region. And what brain fMRI does is it captures these changes in oxygen, given that we know that the process of brain oxygenation works as I just explained. So the theory is that if there is oxygen at this point, then that region worked some seconds before, and that's how you can measure which brain regions were working at any point in the time. So basically, you have these 3D images of the brain across time. So it's a 4D volume in which one dimension is time. So in this case, besides using the structure for solving problems, as I set up in the beginning, the structures itself are important. So the structures are very informative. If I have this structure, then I can know that different brain regions are interacting for some specific process of the brain. And so the problem in this case will be to find the functional connectivity given the brain fMRI data. An interesting thing here is that we try to do it in a fully exploratory way. Some people usually what they do is they assume some region of interest selection, so they reduce the search space and they say, I don't want to focus on the whole brain, I just want to focus on some 5 regions and I want to see how the 5 regions interact. In our case, we want to go for the fully exploratory way in which I don't want to pre-select this set of regions, I want to use the whole brain. But then the problem is that when I use the whole brain, you might end up having 900 variables or up to 45,000 variables, depends on what is the resolution in which you capture the data or the resolution that you're working with. The problem is that learning Bayesian networks and learning MRFs in this context, given the large number of variables, becomes more difficult. But for this specific case, we found out that the fMRI data seems to be Gaussian, so it shows Gaussian properties. And therefore, given the Gaussianity assumption, we don't have these problems, so given the large number of variables, the problem becomes difficult, and I will talk a little bit more later. So let me briefly set up the problem, which is the problem of searching for the best structure, which is basically the common thing across all the work that I will talk about. So here the problem is that given training data, and let's call this training data D, and so we are talking about different samples. Let's call them X1, X2, X3. So we have different samples as training data. First, we have a way to score all possible structures, and this way will be the log likelihood. So if I have a candidate structure omega, the score or the log likelihood of this structure is defined by this formula, the log of the data given the model omega. And this is nothing else than just the average of the log likelihood of every sample in my training data. So this is just the average of all the log likelihoods. And the searching process will be like this. So imagine this is the space of a structure. So at any point in this space will be a different structure. So we have a structure omega 0, omega 1, and we have different structures in the space. And here we have the best structure, the structure that will somehow maximize this likelihood. So the search process will start with some omega 0, then it will jump to a different structure that is omega 1, and hopefully we are hoping that the log likelihood of omega 1 is better than the log likelihood of omega 0, and then we'll continue jumping until we reach the log likelihood of omega asterisk, which is the best structure, and no other structure is better than this omega asterisk. Right? So the searching process will be jumping through different structures until you reach the best structure in your search space. What I just explained is called the maximum likelihood estimation. So we have the maximization of the likelihood omega in this search space of all possible omega. So every time I talk about maximum likelihood estimation, just think about this jumping from different structures until you reach a structure with high score, which in this case is the log likelihood. And we hope in most of the problems to find global convergence, meaning first that we hope that the score is better every time we jump from one structure to the other. So if we go from omega 0 to 1, we hope we get a better likelihood and so on and so forth until we reach this. And we also hope we don't get trapped in a local minima, meaning while we are jumping from one structure to the other, I don't want to reach a path of another structure that doesn't allow me to jump to the best structure. So the two things are desirable so that we can have the global convergence and you are actually obtaining the maximum likelihood of your model. Now, in this searching for the best structure, let me define the best a little bit better. We want this structure not only to have a good log likelihood in the training samples that I am given, we also want this structure to be good for unseen test data, so data that I don't have right now. So, and I want the structure to be good also in the unseen test data. So what we usually do in machine learning is we use priors. So this priors is an additional term in this maximization process that will penalize a little bit the likelihood in this omega in order to make it not reach to the best value of the log likelihood, but the best L minus R, the best likelihood minus the penalty. And what this most of the time does is it allows to get good generalization. It allows to get good performance in unsynthesized data. And we can use this regularizer or this prior not only to avoid overfitting and to get good generalization, but also to impose or to enforce some desirable structural properties. For instance, if I want to learn a graphical model, I would like to learn a graphical model that has few edges. So I don't want a fully connected model with a lot of edges. I might like to get a model with few edges. And in that case, we are imposing sparseness in the structure. So these R might encode any structural property. And in this talk, I will talk about different structural properties that I am trying to impose in the learning. So the talk is mostly about this term. And we call that regularized maximum likelihood estimation. So let me put my research in a context of graphical model. So we have, as I explained, we have two types. We have more types, but I'm just showing two here. We have Bayesian networks and Markov random fields. And let me put another axis into this graphic. So we also have continuous variables and also have discrete or categorical variables. So the work that I will explain today is priors that fall in for Markov random fields and continuous variables, and I will talk about local constancy, variable selection, and multitask. I also have work that was just recently accepted 2 days ago for Markov random fields on discrete variables. I will not talk about this today. I just wanted to show you in the context of the different things that we can do. But here I am talking about convergence rates. So I'm talking how well do we jump from one structure to the other and how fast we reach the best omega asterisk structure. And I have also some work that goes through the 4 different boxes here, which are statistical properties of graphical models. That was in 2011. So you can see how I might need to fill a little bit more places in here. I need more work in these two sides and a little bit more here. So let me explain the main object of the study here are Gaussian graphical models. So let me briefly explain. These Gaussian graphical models are Markov random fields, so it belong to that second family of undirected models. And here we assume that the variables are jointly Gaussian. So if you are familiar with multivariate normal models, then this is exactly the same model. And the good thing here is that the partition function C that I explained that in general is intractable, in this case is tractable. Therefore, the log likelihood is tractable. So we can do search in a very nice way. And let me just explain you this, that on the left side, we have the graph as I was showing in the beginning. So you can see how 1 and 2 are connected with some positive weight shown in blue. 2 and 5 are connected with some negative weight shown in red. So you have these 5 variables, and we can represent this graph also as a matrix, which is symmetric. So as you can see, 1 and 2 are connected with some positive weight. You can see here in the matrix, the column 1, row 2 has the blue edge, and 2 and 5 are connected with a red edge. So you can go to column 2, row 5. They are connected with some red edge. And I'm just assuming that actually in Gaussian graphical models, you want this diagonal to be actually positive, and I will explain later why. So you can see this graph in 2 ways. You can see it as a graph, and you can see it as a matrix. So I'm just showing this because in the next slides I will be talking more about also the matrices. And this matrix, for the case of Gaussian graphical models, is called the precision matrix, which is the inverse covariance. So if you're familiar with what the covariance matrix is, just think about the inverse of that. And we are trying to estimate this precision matrix. And just to make a small difference between the covariance, there is one thing that is called the covariance matrix. That's the parameter that I want to estimate. And another thing is the sample covariance, which is what you compute from a sample. So here I'm talking about the parameter that you want to estimate, that we don't know what the values are for that. So there is a lot of work in regularized maximum likelihood estimation for GEMs. There is work imposing sparseness, diagonal structure. Some people also want to impose block structures, so you have big blocks of squares, where you know how the variables are assigned to blocks and where you don't know how the variables are assigned to blocks. So there has been quite a lot of work in different type of structural properties that you want to impose. Then you will see in the rest of the presentation that I will be talking about positive definiteness. So let me just briefly explain why do we want these Gaussian graphical models to be positive definite. So what happens is that when the precision matrix is positive definite, the probability density function, the p of x, if you plot it in these two axes. So imagine this is a model of two variables. When the precision matrix is positive definite, then you have this bell shape that you are familiar with, for instance, in hypothesis testing. So this is just a generalization of the bell shape that you see in hypothesis testing to several dimensions. When it is positive definite, then you have this nice shape. When it is not positive definite, you have this type of weird shapes. And the problem is not only that the shape is weird, but the normalization constant C in these two cases, when it is not positive definite, becomes infinity. So we don't have a probability function. And that is why we want the precision matrix to be positive definite, to ensure that we are having a probability density function. So let me talk about the first part, is the learning the Gaussian graphical models by imposing the local constancy prior, and this is work with Luis Ortiz, Dimitri Samaras, Nikos Parayos, and Rita Goldstein. So imagine we have data that comes from some spatial manifold. So for instance, think in this case we have a silhouette moving through time. It's a person walking, and we track the silhouette through time. So in this case, each of these points here is a different variable that is moving. But in this case, we have some kind of idea of a spatial neighborhood between these variables. Not only they move through time while the person is walking, we also have some idea of the spatial neighborhood of the variables. Now imagine we have cardiac magnetic resonant images. So we have this, we have the heart that we are tracking through time. And again, you have these points that you are tracking and they move. But not only they move, we also have information on how this point, this pixel here is neighbor of the pixel just below, and so on and so forth. So we have a spatial neighborhood information on our variable. Same for brain fMRI. We have voxels, so we have some neighborhood in 3D. So this local constancy prior was created for this data with the spatial neighborhood. And our idea was that if a node, if one of these nodes that is moving through time, we have some information of this node, this neighbor of this other node that might be far away. So if there is a neighborhood in the graphical model, then the spatial neighbors of this node might also be more likely to be connected in the graphical model to this other node here. Well, what we don't have is this. What we don't want is these two nodes being connected and the neighbors of this is not connected to the other node here. So the spatial neighborhood will impose some regularity in how the things get connected in the graphical model. So the way we did it is we included an additional term to encourage the local constancy. So this first term in this maximization, you can see how this is the same as the maximum likelihood. We have the maximum in a space in which we want the precision matrices to be positive definite. And our term that we are trying to maximize, the first term is the L term that I showed in the beginning. So this is the L of omega, is the log likelihood of the data set. So this is how L looks like for a Gaussian model. And then we have these regularizers that were the R terms that I showed in the beginning. So we have a prior that is the L1 norm for sparseness. So we want this matrix to have a lot of zeros, meaning we want the matrix to have few edges. We want the graphical model to have few edges. And this is an additional term that we included in order to impose the local constancy. Just for making this easier, just forget about this operator. Just think this is a multiplication, and so this omega is This omega is the precision matrix that we want to find. This sigma is the sample covariance matrix. So this is given by the training data. And this D is a differential operator that defines the neighborhood. So in this matrix D, we have different rows, and if the variable corresponding to this column is a spatial neighbor of the variable corresponding to this column, then you will have a row saying -1 here and 1 here, or you can use more general weights in this matrix. But you will have non-zero weights whenever the variable corresponding to this and this column are spatial neighbors. So in this case, you might think, for instance, between this variable and this variable here, you will have a non-zero weight in the row. And we could actually find some interesting properties. By using norm duality, we found that the optimal precision matrix in the problem that I showed before has a minimum eigenvalue that has this form in which n is the number of variables and m is the number of neighbors. Rho and tau are the weights of the penalizers that I showed in the previous problem. So this is the minimum eigenvalue and this is the maximum eigenvalue. And why is this important? Because we want the optimal solution to have a minimum eigenvalue strictly higher than 0, and we want it to have a maximum eigenvalue that is strictly lower than infinity. That means that the graphical model is not only positive definite, it's also full rank, it's non-degenerate, so it's properly modeling interactions between variables. So that's an interesting theoretical property of the optimal solution of the previous problem. If I would get 0 here or infinity here, then I wouldn't even bother in solving this problem, because I know that I cannot guarantee any theoretical property of the problem. The way we solved this problem was a very simple way. We did the block coordinate descent method. So it's a block coordinate descent on the primal problem, in the original problem that I showed in the beginning. And like other methods like covariance selection and graphical lasso, they do the block coordinate descent on the dual problem of the one that I showed before. Basically what we do in this block coordinate descent is we fix part of the matrix at every point, and then we are trying to guess the values. We are trying to maximize the function with respect to this column and row. And more than that, we fix all the light green values, and we try to maximize only with respect to one specific entry. And then we simplify the problem. Then this problem is concave. It's the maximization of a concave function. It's a sequence of quadratic subproblems with closed form solutions, so it's very easy to solve in a computer. I will show algorithmic details in the third part of the presentation, the multitask program, which I believe is more interesting. So one important property that you will see in the three different priors that I will show is that we actually find a sequence of positive definite solutions, meaning that every time we jump from one structure to the other, if you remember my chart showing the different structures that we are jumping to until we reach the maximum, every time that we jump from omega 0 to omega 1 and so on and so forth, all of these structures are positive definite, so that they have the property that I want. So to be more formal, this is the matrix. At any point in time, we are fixing this, and we are calling this W. We are calling this part here, except the last box, Y. And because this is symmetric, then I have the Y transpose here and the Y here, and we are calling this box C. So this is the omega variable that I am trying to find, and then I can do the same with the sigma hat. I can separate it into different variables. And this problem, for some suitable setting of variables A and B, these variables A and B will depend on D, on the differential operator, but it's not important to show exactly how they relate here. So let's just imagine there are some suitable settings of A and B given D. We can actually transform the original problem into this problem here, that you can see has some linear term, has some L1 terms, and some logarithmic term. The interesting thing is that if we maximize this equation with respect to C, you will find that this term c minus this part here is always greater than 0. If I had an initial w that is a strictly positive definite, after finding c, then omega will be also positive definite. So if this is fixed and I find the best y and the best c, I will find an omega that is still positive definite. And this is given by, this is called the Schur complement, the part that is here is strictly positive, and if the w is a strictly positive definite and this is strictly positive, by following the Hainsworth inertial formula, then we know that the omega is positive definite too. So we can guarantee that every time we jump from one structure to the other in our maximum likelihood search, we are getting positive definite solutions. And this applies to all the different priors that I will talk about. So let me show you some experiments. We applied some synthetic, we created some synthetic model with 9 variables and 50 data sets. So you can see these 9 variables, and we put x1 and x2 to be locally constant with respect to x5 and x6 and x7. So you can see how these two relate to the other two, because these x1 and x2 are neighbors and x6 and 7 are neighbors. And we also put x4 and 5 to 8 and 9 to be locally, to have a locally constant interaction. And we also put a non-locally constant interaction between x1 and x4. Why? Because neither x3 nor x5 are interacting with x1. Neither x2 is interacting with x4. Then we also apply this to different data sets. A walking sequence, that is a sequence of 79 frames, 40 manually labeled landmarks. We apply this to cardiac MRI, a sequence of 24 images and 122 manually segmented pixels here that move through time, and brain fMRI, in which we have 16 drug-addicted individuals, 12 control subjects, and we are measuring here through time how the brain responds to conditions of monetary reward. And in this case, we have more variables. We have 869 variables and a sequence of 87 images through time. So in the synthetic experiments of 9 variables, you can see how, I think this is not showing here, it should be the Kalbach-Leibler divergence of our model here, of our method here is lower. So this is the Kalbach-Leibler divergence with respect to the ground truth. So the lower the better. The lower the better you're recovering the ground truth distribution. You can see how in blue I'm showing data samples of four examples, and in red I am showing data sets of 400 examples. So you can see how our method is always better, irrespective if we are talking about large samples or small samples. It's better than the competing methods that only enforce sparsity. We can also talk about precision and recall. So that this means how well we are recovering the edges in the synthetic ground truth model. So in this case, the precision is 1 minus the fraction of falsely included edges, and the recall is 1 minus the fraction of falsely excluded edges with respect to the ground truth distribution. And you can see how our method is, so the higher the better, is always higher than the competing methods that only impose sparseness. And the recall is always better here. We might have not done the best, but we are still fairly, we still have a fairly good recovery. And remember that the blue is the hard problem in which we only have 4 samples and 9 variables, so we have very few number of samples with respect to the number of variables. And this is a measure of the Frobenius norm, which is another measure that in the paper that I was talking to you about the statistical properties, this Frobenius norm is actually very related to the Kalbach-Leibler divergence for graphical models. So it does behave very similarly to the Kalbach-Leibler divergence. If you just remove this model, which is the fully independent, no edges between them, you will see that these curves actually resemble the curves that you have here. So again, the lower the better in this case too. And let me show you just quickly some examples of how we. This is how we recover this. This is how we recover the structures from a walking sequence. You can see how the hands connect to the feet, and how different points in in the leg are also connected. So they disconnect negatively because the hand is doing something that is opposite to the feet. And in the same leg, you can see how things are going in a positive way because all the leg is moving the same way. And let me show you the heart. So this is the heart pumping. You can see how the different points move through time, and because all these points move together, they have some positive interaction, these two, and there is a negative interaction between the two walls of the heart. So it is finding structures that make sense. And these are the results in functional brain MRI. Remember, these were conditions of monetary reward. Interesting thing here is that you can, we highlighted two areas, the prefrontal cortex and the cerebellum. You can see in the drug-addicted subjects, there is very few prefrontal cortex region being highlighted and a lot more in the cerebellum. And in the control subjects, you have more areas. You have more areas in the prefrontal cortex than in the cerebellum. First, you can see how there is a kind of dialogue between the prefrontal cortex and the cerebellum, and we believe that this is because the prefrontal cortex tells the person to take long-term reward decisions, while the cerebellum tells the person to take short-term reward decisions. So, given monetary rewards, then it makes sense that there is a dialogue between these two regions. And it is interesting how drug-addicted subjects have less interactions in the prefrontal cortex, which are the long-term reward decisions, and more in the cerebellum, which is the short-term reward decisions. So we also evaluated the log likelihood in a test set. So we used part of the data set to do the training and some different part for doing the testing. And this was a 5-fold cross-validation setting. So here we show how the best method is shown as 1, and then the other methods with respect to the best. You can see how our method, which is the one in red, the last one, is consistently better than all the other methods. And it was interesting how all these other methods, like Milhausen-Bullman, covariance selection, and graphical lasso, don't do consistently better than a method that is fully independent, a method in which I have a structure that has no edges. You can see how, in our case, we always do better than a structure that doesn't have any edge. But in this case, for instance, learning the edges actually hurt the process. And learning the edges doesn't do better than assuming that there is no edge at all in the structure. So that was an interesting finding also. So let me jump quickly. This is work that we just presented in Spain. This is joint work with Irina Rich and Guillermo Sechi from IBM. So we're going to a different type of prior here. And here, let's think about data sets in which we have thousands of variables. So for instance, gene expression, stock prices, world weather. We're talking about 8,000 of variables or 3,000 of variables. And the type of prior that we want to enforce here is that only a small number of nodes will interact with each other. And this is a similar idea to what people do in classification, in which you don't assume that all your features are important for some classification problem, but only few number of features are the important ones for performing classification. So here, instead of having this type of structures that are just sparse, so there are just few edges, but the edges might come from different nodes in the structure, we want to find this structure in which there are very few nodes that are connected, and very few edges among these few nodes that are connected. And we have a lot of nodes that are totally disconnected from the rest. So given that we are applying these to thousands of variables, it sounds reasonable to do the selection of this small number of variables, and maybe, I don't know, maybe 50 or 20, and then trying to find the connectivity between this small number of variables. So in this case, we have a similar problem. We have the log likelihood part as before. We also have the sparseness prior with the parameter rho, the L1 regularization. And we have added this variable selection prior, which is the L1p regularizer. So basically this will try to make entire rows of the matrix equal to 0 to make that specific variable independent of the rest. So we have actually focused in two values of p. We have focused in 2 and infinity. You can actually extend this to any p bigger than 1. And this is the definition of the L1p. This is basically the LP norm, the sum of the LP norms of all the different rows. And you can relate this to regression and classification, in which the p equal 2 case is the group lasso and the p equal infinity is the simultaneous lasso. As before, we can also show this property of the minimum and the maximum eigenvalue. So that's still a nice property also for this problem. And also, if you do block coordinate descent, you find something that is maximization of a concave function, which is good. This is still also a sequence of quadratic subproblems with closed-form solution, but also I'm keeping the details for the multitask, which I think is more algorithmically interesting. Let me go through synthetic experiments. In this case, we generated 50 random structures. For each of these structures, we generate 50 samples, and we are talking about 200 variables in this case. And we assume that 50 of these variables are the connected ones. These are the yellow variables that are important, that have connectivity between them. And for these 50% of the variables, which in this case is 100, we generate 80% edges between them. So not all of them are fully connected, but only 80% edges. And in the paper, actually, we use also different values, like 20 and 80 in this case, and 20 and 50 in the case of the edge density. And for those structures, we generate random edge weights that are between -1 and 1. You can see how this is showing the ROC curve. So if you have a curve that is like this, going through the corner, that means that you have perfect recovery of the edges in the ground truth model. If you have something that is diagonal, that means that it's totally random. You are not recovering very well the structure. And here you can see, in this case, is what we call the high variance confounder. So the confounders have as much variance as the connected variables. You can see how the recovery of our two methods, L12 and L1 infinity, is better. And this is showing the Cardiotonic divergence with respect to the ground truth. You can see how the KL divergence is also lower than the rest of the method. So we recover the edges better, and the weight of the edges are also good because the probability distribution has lower KL. This is the other regime, which is the regime of what we call the low variance confounder. So these additional variables that has no connectivity have a variance that is 10 times lower than the variables that are connected. You can see here that the recovery is almost perfect for our two methods, the L12 and L1 infinity, while the rest of the methods still cannot handle that case. And actually, one of them, the covariance selection, does a lot worse than chance, which is another interesting observation. And the Cardiotonic divergence of our two methods, L12 and L1 infinity, is better. And then we try this method for different data sets. For instance, the brain fMRI of 16 cocaine and 12 control subjects. Just notice that we are trying to find edges between these variables. So if we have 869 boxes, we are talking about 377,000 parameters, possible edges that we are trying to recover, and that's a hard problem. And you can see how here I'm showing the negative log likelihood, so the lower the better, how our method has better negative log likelihood with respect to methods that only impose sparseness for addicted subjects as well as for control subjects. Here I'm showing one of the other important point that we want to make. It is not only that we want to recover things that have better log likelihood, it's also that we want to recover things that are more interpretable. So here in the top you have the structure for cocaine and control. So in the top you have the structures from our L12 method. You can see very few edges, and you can also see the regions again, the prefrontal cortex and the cerebellum. And here also some other additional regions working in this case of control subjects. Well, a different structure that has fairly the same amount of density, so fairly the same amount of edges, is more complicated to interpret. So here you can interpret this as a dialogue between different brain regions. Here is hard to interpret from a neuroscientific point of view because you have almost all the brain being connected. And also we tried classification. So if you have a subject that you didn't use for training, you can guess if I use this model, I get some probability. If I use this other model, I'll get a different probability. So I can use that for classification, the model that gives me higher probability. So if I have an unseen subject and I compute the probability here and here, if this gives me higher probability than control, then I classify the subjects as cocaine. And by doing that, we found that almost all the methods actually obtain 84.6% classification. So we are not hurting the classification accuracy, but we are getting structures that are more interpretable and have lower log likelihood. Now, we wonder what happens if we actually train these structures for doing classification. Remember, we have used these structures trained independently, so we learn this structure, and independently we learn another structure. But if we try to learn to perform classification, I have actually no idea what would happen, and if the priors that I am proposing would have maybe better performance. We also tried this to gene expression data. This is around 8,500 variables, around 36 million parameters, and you can again see how our methods outperform the methods that only impose sparseness. This is data from NASDAQ stocks taken from April 2010 to April 2011. This is 2,700 stocks, 3.7 million parameters. You can see how our log likelihood is better than the rest. And this is world weather. So we have data of monthly measurements of temperature, precipitation, vapor, cloud cover, wet days, and frost days. This is from January 1990 to December 2002. And we are talking about around 4,000 variables. So this is weather across all the world. Of course, in this case, you might have used also the local constancy. I haven't shown the results here. But remember, our variable selection prior doesn't assume that there is an spatial neighborhood in the data, so it's more general. And in this case also, we get better log likelihood compared to the rest. So you can see how this idea of having better log likelihood is consistent across very different data sets, not only brain, but also the stocks, world weather. So it seems to be a very general prior, and the idea of variable selection seems to be important. And let me just jump through the last prior that we came up with, and I call this learning the multiple Gaussian MRFs. So this multitask learning things from multiple data sets that have some relationship between them has been used in different settings, in regression, classification, compressive sensing, etc. Our idea here is that we are trying to learn several matrices at once. And instead of imposing sparseness, we are trying to impose sparseness in the direction of the tasks. So imagine this task might be one person, so each task is a different person. And we're trying to learn structures that will have the same sparseness pattern. So if this is 0, it's very likely that it's 0 for everybody else. So the penalty goes in this direction. And now we have then the superscript k, which means this is the sigma hat for the task k, and again we are trying to find different omegas for all the different tasks. So the likelihood is the summation of the regular maximum likelihood is the summation of the different likelihoods for each task, plus our regularizer that we have, which is the maximum for every edge across tasks. And that is why I said that we are regularizing in this direction. So we take the maximum value in this direction. And again, we can show similar minimum maximum eigenvalue properties for this problem. And we also perform the block coordinate descent. In this case, there are more interesting properties. It's actually probably convergent given the results in CEN 2001, given that the penalty is separable by edge. And we perform the same task of going through the last row and the last column. And for some suitable setting, if we do the derivation, if we focus only in this, you will find out that this is the L infinity regularized quadratic problem. So this is the quadratic part and this is the L infinity part. The interesting thing with this problem is the dual of the problem. It has a very interesting geometric interpretation. So from this problem that has x as unknown, we can go to this other problem, which is the dual that has y as unknown. So this is still a quadratic, but now what was a regularizer becomes a constraint. And this is how you compute the best x given the best y. And there are two cases. The case in which this c variable, the given c variable here is, the L1 of this c variable is lower than rho. So that means that the optimal y is inside this diamond, inside the L1 wall. And the interesting case is the case 2 in which the L1 norm of c is higher than rho. So in this case, the optimal solution is outside the diamond, and what we have to do geometrically is we need to inflate a balloon given some properties of Q until you hit a point in this diamond here, and that's the point that defines the optimal Y. I will skip the details of the algorithm. I will just say that this ends up being a continuous quadratic Naxa problem. It has very interesting properties, meaning that the only thing you need to do in order to do the maximization and finding the best y is you need to sort some values in this direction, and then you need to find in this y-axis where rho is. And once you find that, you know what is the optimal breakpoint, and given that, you find the optimal c, then you find the optimal y, then you find the optimal x, and then you can go back to the original problem. This has been solved. Actually, it was interesting because this was solved by different people since 1980, and this was unknown somehow in the machine learning community until I published this paper. Interestingly, there was a paper in 2008 that was claiming some nice properties, but I think this mathematics community, this paper from the mathematics community was not known by the machine learning community. And doing all this derivation, we can find a very simple solution that just relies on sorting. And this is actually a generalization of a 2009 paper given by Liu, in which he talks about a winsorization operator. We also extended this to p equal 2, besides the p equal infinity that I shown you before. And this problem was originally formulated by Markov in 2010. So we have generalized our initial problem to this. So here I will show you some results in synthetic experiments. We are talking about 5 tasks, 50 variables, 50 random structures, and density of 30% of edges, and random weights between -1 and 1. You can see how the recovery of edges in these ROC curves is better for our two methods, even better than the method that was proposed in Varocco 2010. Although the problem is the same, our method for solving the problem is different, and it gets better results. And Calvert-Gleiber divergence, we get better results too. And this is results on brain fMRI. Here, each task is one of each repetition. We are doing 5-4 cross-validation on the subjects. So we use 4 fifths of the subject for training and 1/5 for testing in 5 rounds. And you can see how the L1 infinity and the L1-2 perform better than the rest. So the best of this is better than the best of the other methods. And furthermore, you can see that our L1-2 method is always better than the L1-2 method in red here of Varocco. So our method for solving the problem is better than their method. So this happens for cocaine-addicted subjects and also for control subjects. And here I wanted to show what was the initial motivation, which is also interpretation. So you can see how I picked three random subjects. So this is subject 1, 3, and 5. And for each of these 3 subjects, I have picked 10 regions at random. And you can see, for instance, for our L1 infinity method, the L1 multitask method, L1 infinity multitask method, you can see how the structure across the 3 different subjects is the same, so the topology is the same. You will see some difference in the edges. For instance, this edge is positive while the edge for subject 3 is negative, but the topology is the same for the 3 subjects. And the L1, 2 also, the topology is the same across the 3 different subjects. Now, if you apply the upper bound method of Barocco, you will find that it doesn't lead to the same topology for the 3 subjects. And if you apply a sparseness promoting method, then you find structures that are very different. And why we believe this is important is because for neuroscientists, interpreting structures across different subjects that are the same is might become simpler than interpreting structures that are totally different. So here, you might just focus on how the different brain regions are interacting and maybe focusing why this is positive for this subject and why this is negative for this subject, while the topology might have some explanation. But here, if you will have a different interpretation here than in here because it's just a completely different structure. So here our point was also on the interpretability of the models besides giving better results. So the take-home points here is that graphical models are an important tool for different areas. Besides that, structures are very informative in areas such as neuroscientific research for interpretation. So it is not only that you can use the structures for inference, you can also interpret the structures by itself without using these structures furthermore in any inference problem. We hope that learning structures may also extend the use of inference as the problems that I showed in the beginning to problems in which we don't know the structure a priori. And that is work that we are trying, that we are doing right now with Kibon Yoon partially. We have proposed different structural priors that we believe are reasonable and lead to better structures. And finally, we have shown some theoretical properties and probably convergent algorithms. I want to thank different people, Nikos Parayos, Jordan, Sirina Rich, Guillermo Seshi, the last 2 from IBM, Nikos Parayos from Ecole Centrale, and people from Brookhaven National Lab, Dardo Tomasi, Nelly Clayton, Maloney, Scott Mueller, and Akonova for making this research possible. Thank you.